Hey everyone. So there's just a few more things in this section on complex numbers that we need to wrap up. So first of all, here dealing with the division of complex numbers. Eventually here I will walk you through some problems where we can learn how to divide a complex number with another complex number. But before we do so, there's one thing that we need to know, one term that we need to understand that'll help us with the division. So whenever we have some complex number, a plus bi, so we have that number in that form. And then if you take the same real number component, but then you make the imaginary component its opposite, so then we get the complex number a minus bi, then that number and that number are what we call conjugates of one another. And because they're complex numbers, we oftentimes will refer to them as complex conjugates of one another. So basically, all that a conjugate is it's going to like plus the imaginary part in one of the numbers, and then it's going to minus the imaginary part in the other. But the real part's always going to stay the same sign. So there's something really interesting that happens whenever you have two complex conjugates. So I'm just going to make up an example. So let's say that I have a complex number that has -3 as its real part, and then let's say plus 4i for its imaginary part. Then in the other bubble here that I'm going to multiply with, I'm going to write the complex conjugate of that number. So it's going to have to be the same real number, but then we'd have to switch the sign of just the imaginary part. Okay? So those two numbers that I've written are complex conjugates. So let me now multiply these two numbers, which really just kind of got to think FOIL, right? So if I do -3 times -3, you're going to get 9. And then if you do -3 times -4, that's going to be a positive 12i. And then if you do positive 4 times -3, that's going to be minus 12i. And then finally, if you do positive 4 times -4, that's going to be minus 16i squared. Just like that. All right, so we're going to be able to simplify that out a little bit here. So we'll be able to note that this guy right here, I to the second power, is actually just -1. So that means that -16 is going to multiply with that -1 to equal positive 16. So we can actually take this positive 16 and this positive 9 and add that together to make 25 then. And then finally, you'll notice that right there, 12i minus 12i equals 0. So we really just get 25 plus 0, which equals 25. Interesting, right? So we multiplied two complex numbers and we actually just got a real number answer. So that will actually happen when you multiply conjugates with one another always. So right here, right, I've written that the product, or in other words, multiplying two complex conjugates is always a real number. That'll always happen. And we can kind of prove that just most generally, so that if you think of any complex number, a plus bi, and then a minus bi, which of course is the conjugate of it, you'll be able to see that if we do like FOIL this out, where you get a squared, and then a times -bi would be minus abi, and then bi times a would be plus abi, and then bi times -bi would be minus b squared and I squared. Then what'll happen with that then is right here, minus abi and plus abi will equal 0. And then right there, you'll just have your a squared. And then right here, since I squared is equal to -1, then negative b squared times -1 will actually result in plusing b squared. So you'll actually just get a result of a squared plus b squared. So like you'll always kind of get that when you multiply two conjugates, complex conjugates. And so yeah, that's a real number, right? There isn't anything imaginary in a squared plus b squared. It's just real numbers. So that kind of proves it for us. Okay. All right, so that's useful to know because now we want to learn how we can divide a complex number with another complex number, right? So as it says here, it says to divide and then express each quotient as a complex number in standard form. So I've said that we always want to make sure that whenever you express a complex number answer, that it's always of the form a plus bi, right? The real number at the front and then the imaginary part at the end. So right here, you just have to realize that we are taking some sort of a number, just like a red number, and we're dividing it by a blue number, okay? So to actually like figure out how many times 3i goes into 9 plus 12i, right? So how many times the blue number goes into the red number, what we'll do, it won't actually kind of really look like dividing, but this is how we divide it. So what we're going to always do whenever we're trying to divide complex numbers is you're actually going to multiply, but you're going to multiply by 1, okay? Because it's not going to change the value of the number, right, when you multiply by 1. What you're going to actually really multiply by, though, is you're going to multiply by this. So the same thing over the same thing, and what you want to do is you want to look at the denominator. So in other words, the thing you're trying to divide by, and you want to use the complex conjugate of that. So if you think that this number really is 0 plus 3i, then its conjugate would be 0 minus 3i, or just negative 3i. So what I want to do then is I'm going to use negative 3i over negative 3i, which is just equal to 1, right? And I'm just going to multiply by that. So what will happen is, like, if I put that in parentheses, the negative 3i is going to distribute to both of those couple things, right? So on top, you're going to get that if you multiply by the negative 3i. And then on bottom, if you do negative 3 times 3, you're going to get negative 9, and then I times I, which is I squared, right? Okay, so we want to just make sure that then this just gets simplified all of the way, of course, right? So what'll happen is that on the bottom, you're always going to get a real number because we chose the complex conjugate of what was on the bottom. So since I squared is negative 1, and then we multiply it with negative 9, we actually just get a denominator that's a positive 9, okay? And then on top, I'm going to put the minus 27i over here. And then the negative 36i squared, well, since I squared is negative 1, it would times with a negative 36 to equal a positive 36, right? All right, so it equals this. So the last thing is that we want to make sure we have a separate real number part and a separate imaginary part. So I want to make sure that I rate this as 36 ninths, so I have a separate real number part, and then minus 27 ninths I, so I have a separate imaginary part. And then if it turns out that you might be able to reduce that, and you might be able to reduce that, then make sure you reduce those fractions. And in both of those cases, you are able to do so. You're going to be able to get 4, and then minus 3i. So that right there is in standard form, and this is the answer to the division problem, right? So just kind of thinking conceptually about what is happening here, since we did 9 plus 12i, and it got divided by 3i, and the answer to that was 4 minus 3i, right? Then just like we know with, multiplication and stuff, then if you were to do like 4 minus 3i, since it was the answer to the division, and then multiply it by 3i, right? You're going to FOIL that out, that sort of thing. It should equal 9 plus 12i, right? So that relationship should all hold, okay? Excellent. All right, so now that you kind of got an idea what's going on, you can cruise just a little bit faster through some of these here. So this is 13 divided by negative 6i. I'm just going to rewrite it as 13 on top and then divided by negative 6i on bottom. So all you'll need to do is just multiply by a fraction that uses the conjugate of the bottom, right? So since the bottom is negative 6i, its conjugate is going to be 6i. So I'm just going to multiply by 6i over 6i. And then, yeah, so it's just that times that. If you put that in a calculator, you're going to get 78i. And then on the bottom, if you do negative 6 times 6, you're going to get negative 36. And I times I is I squared. So you end up with that. And then the bottom actually simplifies nicely because I squared is negative 1, which then times this with negative 36 to equal a positive 36. So you really just end up with 78i over 36. So there isn't a real number part to this answer, I guess, just this imaginary part. If we could reduce the fraction, you would definitely want to. It does turn out that I think you can divide both 78 and 36 by 6 because it's going to go in 13 times into that and 6 times into that. So you should end up with a final quotient there of 13/6i. All right. So this is also another division problem. And so this one will just be a little bit more stuff because now for the first time in examples here, I have a number on bottom that has both a real and an imaginary part. We haven't had that yet. So if I wanted to just figure out the answer to this division problem, all you need to do is just multiply by a fraction that uses the conjugate of the denominator. So the conjugate would still have the same real part, but then it would switch the sign of the imaginary part, so it'd be plus 4i instead. And you'll have the same thing on the bottom right there, 1 plus 4i. So it's going to be a little bit of work because you're going to have to FOIL out all the stuff on top, and then we'll also have to do that on the bottom. I'm going to start with just the top part. So 2 times 1 is going to be equal to 2. And then 2 times 4i is plus 8i. And then 3i times 1 is plus 3i. And then 3i times 4i is plus 12i times I squared. All right, so that FOILs everything up at the top. And then on the bottom, if I FOIL that all out, 1 times 1 is going to equal 1. And then 1 times 4i is going to equal 4i. And then negative 4i times 1 is equal to negative 4i. And then negative 4i times 4i is going to equal negative 16i squared. So we basically end up with all of that red stuff on top of that green stuff right there. And we just got to like combine like terms and simplify and everything. So I'm going to start on the bottom, because what should happen on the bottom is it should just be a real number, because we did a conjugate times a conjugate, and you'll see that happen because 4i and negative 4i will cancel out. And then if that right there is just negative 16 times negative 1, since that's what I squared is, then it's really just a positive 16. So you're going to be able to take positive 16 and 1 and add together. So you're really just going to end up with a denominator of 17 then, because that's 1 plus 16. And then on top, if I add the imaginary parts together, you're going to end up with 11i. And then that right there is really 12 times negative 1. So you're going to end up with a negative 12, which then if you take the negative 12 and the 2 and you add it together, you're going to get negative 10. So we end up with negative 10 plus 11i on top over 17. Then you got to make sure that you write that as a separate real and imaginary part. So then you're going to have the negative 10 17ths and then the 11 17ths I, like that. And then if you can reduce that fraction and reduce that fraction, then definitely do so. You can't reduce either of those two fractions, so then you can just leave it as it is. So that right there would give you the quotient. There. Okay, and the last one here, I don't think I'm going to work it out all the way, but just in terms of how would you start this one, just make sure that your starting point would be multiplied by the conjugate of the bottom. Using that. So since the bottom is negative 8 minus 7i, you got to make sure that you still have the negative 8 to start it off, but then you'd have to switch the sign of the imaginary part. So you're going to multiply by negative 8 plus 7i over negative 8 plus 7i, right? So the process of that one is going to be the same as what we did there. You're going to have a bunch of foiling and simplifying and all that sort of stuff with that one. So I'm just going to keep proceeding forward here on to kind of the next stuff. So just note right here that this is kind of a fancier way of looking at complex numbers a little bit, because ultimately you really just do kind of have a complex number right here, because you can just think about this as being 9 plus, and then since your square root is negative, it's imaginary, and then the square root of 4 is 2, right? So it's actually just positive 2i right there. And then also similarly here, that's just going to be 5i. So you could just have negative 2 plus 5i. So the operation that we're doing with these two complex numbers is we're subtracting them. So that subtracting, right, has to distribute. So that means you're going to end up actually adding the 2. And then subtracting a positive means you're actually going to subtract the 5i. And then from there, you just need to combine kind of like the like terms, right? So the 2i and the negative 5i could go together. That's going to make negative 3i. And then also you're going to be able to take the 9 and the 2 and add those things together, and that's going to make 11. So you get 11 minus 3i out of that, right? So that's kind of a similar thing that would apply in this sort of a case. So again, keep moving forward here, going to kind of skip past that, and then jump to here. So now there's an equation right here, and we want to try to solve this, okay? So this looks like a nice equation that we could maybe try to square root and solve, but we got to make sure that we get the n squared alone. So that means if I get the n squared alone, I'd have to subtract 49 to both sides, and then you would end up getting n squared equals negative 49, right? So if you use the square root property, then if you square root that, and then if you square root that, then you're going to get n, and then it'll equal both plus and minus the square root of negative 49. Well, since we're now square rooting a negative number, it's going to be imaginary, and then we know the square root of 49 is 7, so you actually get these two answers right here, positive and negative 7i. So those are the solutions, and then I just want to give you some intuition into understanding why that actually works as it does. So the original problem was that n squared plus 49 is supposed to equal 0, right? So either 7i or negative 7i is supposed to work. So let's suppose we take negative 7i, right, and plug it in. If I plugged it in, then this would be negative 7i times negative 7i. So the negative 7 times negative 7 would equal 49. But then you also have the I times I, which would make it I squared. And then what we know about I squared is that I squared is actually equal to negative 1. So then you would get 49 times negative 1, which would equal negative 49. And then lo and behold, right, negative 49 plus 49 does equal 0. So you can see that indeed negative 7i is the solution. And the same thing would hold true for 7i as well. Okay? All right, so just looking at some other examples right here, I'm going to add 36 and divide by 2, so I get the c squared alone. So if I add 36, first of all here, you're going to end up with negative 64 on that side if you add 36. And then if you divide by 2, you're going to get negative 32 is equal to the c squared, okay? So similarly, we can do the square root property right here. So I'm going to square root that, and I'm going to square root that. So we know for sure we're going to get plus and minus because we're square rooting. And we're also going to get something imaginary because it's square rooting a negative number, and then it'll be the square root of 32. We know that 32 is not a perfect square, but we're going to be able to simplify that radical 32 because it has a perfect square inside of it. The biggest perfect square that goes into 32 is actually 16. So I'm going to be able to write that as I and then square root 16 and then 2 because 16 times 2 is 32. And then finally, since the square root of 16 is 4, we're going to be able to write that as plus or minus 4i root 2 in simplest radical form. So that gives you the solutions right there for the values of c that make that equation true. Okay? All right, and then jump into this guy right here. It looks like the negative 3, I guess, could distribute. So why don't we distribute and get negative 3t squared, and then negative 3 times 15 would be minus 45, which equals negative 6. So then I'll do a couple steps right here. I'll add 45 first. So I get the negative 3t squared alone, and then that's going to equal 39 if I add it to negative 6. And then if I divide by negative 3, then t squared is going to equal negative 13 when you divide by negative 3. Okay, so if you square root that and you square root that, you're going to end up with t squared is going to equal plus or minus, and it'll be imaginary, and it'll equal the root of 13. Now, 13 doesn't have any factors other than 13 in itself, so there aren't going to be any perfect square factors of 13. So it's actually in simplest form as it is right here. Actually, I wrote the t squared. That should not be there, so I'm going to erase the squared because, yeah, it's just t now. So, yeah, there we go. That's the correct solutions for t. Okay, and then a couple more examples here of solving. So what's maybe a little bit different right here is that if I'm going to try to solve for the variable a here, I'll realize that a is kind of in that bubble, but it's also being squared. So eventually what I want to try to do is I want to try to square root that bubble, but we got to get that bubble kind of isolated there all along. So what I'm going to do here first of all is I'm going to subtract 9, and then after I do so, then I'll divide by that 4 that's in front of the bubble. So the result of just subtracting 9 gives me that, and then I'm going to divide both sides by 4, so that then finally we get this a minus 8, that quantity squared alone, and that's going to be equal to negative 9/4 then, which we'll just leave it as a fraction. Okay, so now I can do the square root property, so I can square root that, and then I can square root that fraction as well, which then means that you're going to get plus or minus the square root of that fraction. Now that fraction is negative, so it will be imaginary, and then think about like the square root of 9/4, right? So we know that breaks one of the rules because you're not supposed to have a fraction, right, as the radicand. That's the rule number 2 that we've talked about. So what we could think about then is that that's the same thing as the square root of 9 over the square root of 4, right? Now, it just so happens, actually, in this example, that the square root of 9 and the square root of 4 give you very nice whole numbers. So since we know that that is just 3, right, and that is just 2, it actually is just going to become then 3 over 2, right, or just like 3/2. So really, you should put the 3/2 kind of in front of the I, so it'll be either positive or negative 3/2 times I. So that there gives you the solutions for that equation there. And then one more example here. This one also kind of has the bubble thing going on right there because you got the y plus 6, that quantity squared. So eventually I'm going to want to try to do that to help me try to solve for the y value here. And so, so I just realized one kind of tiny little detail here, guys. Sorry. So I realized that I didn't write the -8 right there. So what I should have had is then if I add 8 and I add 8, I should have the 8 plus or minus 3/2 I. All right, sorry about that. Missed that part right there. Just realized that when I looked at this guy here. Okay, so jumping back to this guy right here. Yeah, we want to get the y plus 6, that quantity squared all alone. So I'm going to add 43 to both sides here first. And that's going to give me 40, which is going to equal -2 times the quantity of y plus 6 squared. And then I'll divide by the -2. And that's going to give me then -20 equals the quantity of y plus 6 squared. Okay, so now that I isolated that bubble, I will take the square root there and take the square root there. And so I'm going to get both plus and minus of whatever there, and it will be imaginary. And then I'll write the square root of just +20. And this time I won't forget the plus 6 on this problem. All right, so there we go. We got the y plus 6 there. So yeah, then if we want to get the y alone, we just need to subtract the 6 to both sides, which then means you get -6 plus or minus the I root 20 is going to equal the y. You see I didn't write the I square root 20 because we can actually simplify square root of 20 because it's the same thing as the square root of 4 times the square root of 5, where that square root of 4, right, is going to result in just a 2. So I'm going to write this as plus 2I root 5, which would be a simpler form of the square root of 20. So that right there is going to give us those two complex solutions for the value of y. Beautiful. All right, so one kind of last thing, and then we'll kind of wrap things up here. So it does turn out that we can use complex numbers to actually like factor expressions and stuff. So a similar sort of expression that we've learned to factor that's different than x squared plus 81 is like x squared minus 81, because it is equal to, if you FOIL out x minus 9 with x plus 9, and you FOIL that out, that's going to equal x squared minus 81. So we've never actually factored anything like x squared plus 81. We've considered that to be prime when you have a sum of squares when you're trying to factor that. But it actually does turn out that you can actually factor like something that's a perfect square and a perfect square that's added together, and you can do so using imaginary numbers. So it's actually almost like kind of the same as what's going on right here when it's x squared minus 81. It's just that instead you're going to be able to factor it as x minus 9i and then x plus 9i. And that does factor this expression here. And so I'll go through the foiling just so that you understand that it actually works. So yeah, if you do the x times x, it's going to be equal to x squared. And if you do x times 9i, it's going to be plus 9ix. And then negative 9i times x would be minus 9ix. And then negative 9 times 9 is negative 81. And 9 times I is I squared, right? So what's going to happen then is this right here, just is going to be x squared. And then right here, the plus 9ix and minus 9ix just equals 0. And then that right there is negative 81i squared. But since I squared is negative 1, the negative 1 times negative 81 is going to equal positive 81. So it'll be plus 81, which means that you get x squared plus 81. Right? So it checks out okay. And that factors that nicely. Okay? All right, so we're going to try to factor this guy right here. So as with any factoring, always check for a GCF first. And I don't think 64 and 25 have anything. But you'll realize that the beginning term is negative, so you at least want to make sure you factor out a negative 1, which means that you get positive 64n squared and positive 25 inside of the parentheses then, once you factor out that negative 1. And then you'll recognize that actually 64 is a perfect square and 25 is a perfect square. And so, yeah, you'll want to hopefully maybe think that possibly 8n times 8n would work to give you 64n squared, right? But in order to get plus 25 rather than minus 25, you would want to use imaginaries. And so if you do minus 5i and then you do plus 5i, it should work out okay. And so that right there, negative 1 times the 8n minus 5i times the 8n plus 5i, does indeed factor it out okay. So just to kind of check this out, you get 64n squared, and then what will happen right there is that's going to give you plus 40i, but that's going to give you minus 40i, so it just cancels. And then that last part right there would be negative 25i squared, but since I squared is negative 1, right, you do get 64n squared plus 25 inside the parentheses, and then there'd be that negative. So it works out great, right? Okay, so we jump to this fella right here, and again, we're trying to factor this. 20 and 45 are both divisible by a common factor of 5, I believe would be the greatest. So you'll want to make sure you factor out a 5 from both, leaving you within 4r squared, and then 5 times 9 is 45, okay? And then you'll realize that then in the bubble, you've got 4 and you've got 9, which are perfect squares, right? So you could do 2r, and 2r to multiply to equal to 4r squared, and then to multiply to equal to 9, you'd want like 3 and 3, but since this is a plus, then you'd want to make sure that you have 3i and negative 3i, so one of them plus 3i and one of them minus 3i, and then that would be completely factored there. All right, and then finally for this guy right here, this is another one where actually that's a perfect square because it's y times y. And that's also a perfect square, that number, 1 over 16, because it would be 1/4 times 1/4, and they're plussed. So to factor this, you can just factor this as y plus 1/4 and y minus 1/4. But in order for that to actually be a plus 1/16, then rather than a minus 1/16, you actually need it to be 1/4 I, and minus 1/4 I, right? And that's going to get that factored. So just realize the difference here, guys, that when that's a plus, right, and you're factoring kind of the sum of squares, you're going to need the i's. So if I had given you like y squared minus 1/16 to factor, then you don't need the i's, right? You can just do y plus just the real number 1/4, and then y minus the real number 1/4, and that's going to be able to factor that expression then correctly.